Okay, we're gonna get started. So what's on tap for today in terms of study assignment is a redox activity, and it's a little bit more complicated than what is in sort of this chapter about redox. So this is going to be our in-depth look at redox reactions and how to balance them properly, like you have to do in this study assignment, so that you'll be able to do that. We then will next time kind of finish up talking about redox reactions in terms of classifying reactions as a certain type of redox reaction. So redox reactions, as we talked about a little bit earlier, really account for the type of reactions that involve really a transfer of electrons. And again, that is one of the three reasons, as we talked about, why a reaction takes place, is this sort of transfer of electrons. And it is really kind of the second big category of reactions, just like double displacement that we started talking about, obviously, is a big category of reactions. Redox is also a big category of reactions, as we will see next time. Uh, some of the more specific reactions that fall under redox are synthesis reactions, decomposition reactions, combustion reactions, and single replacement reactions. So these kind of more specific classification of reactions are all ultimately a redox reaction that's occurring. But again, this is a more kind of specific way of classifying a reaction. So what does redox mean? Redox really does mean oxidation and reduction. And oxidation and reduction, they always occur together, which means if somebody is being oxidized, somebody else is also getting reduced, and vice versa. The nice thing about that is if you could at least identify one of those two things happening, the opposite things happening in the other thing. So you don't have to necessarily identify both of them. If you can at least figure out one, you can know what's happening in the other one. Some definition of oxidation and reduction. There are actually like three different definitions, but we're going to focus in really on the definition that we use most of the time in general chemistry, and that is oxidation means that you have losing electrons, and reduction means that you gain electrons. If you go on to organic chemistry, you also talk about oxidation and reduction in the vein of, did it gain oxygen? Did it lose oxygen? Did it gain hydrogen or lose hydrogen? So those are some other sort of definitions. We don't deal too much with that here in general chemistry, but definitely when you go to organic chemistry, you deal with more, not so much electrons, but more about the oxygen and hydrogen definition. And sometimes people remember this as Leo the lion goes grr, right? Loss of electrons, oxidation, gaining of electrons, reduction. People nowadays are fond of the oil rig, right? Oxidizing is losing, reducing is gaining. Put Leo the lion on the oil rig and it goes grr. You don't have to choose. You can just use them all together in one big swoop there. Now, what does it mean when somebody loses an electron or gains an electron? When somebody loses an electron, they then become more positive, right? Because they now have less electrons, more protons. And if somebody gains electrons, they now become more negative than they started with because they've gained negative electrons. So a really easy sort of way to figure out, for example, is this thing kind of going through oxidation or reduction, is you could just use like a basic number line, and usually on a basic number line, there's a zero. And usually to the right of zero are positive numbers, to the left of zero are negative numbers. So if somebody loses electrons and goes through oxidation, what you will notice with their oxidation number is as it goes from reactants to products, it will actually become more positive, and it will move in this positive direction along the number line. And that will tell you that that thing is going through oxidation. Now, if you gain electrons, like I talked about, you will become more negative. And if you look at their oxidation state, which we'll talk about shortly, and it's moving in this direction, the kind of the negative direction, that thing is going through reduction. So just to show you how this can sort of work, if we take a type of redox reaction, which is a synthesis reaction, like so. And I'll even balance it like a good chemistry student there. Maybe a 2 there to truly balance it. Yeah. And if we look at this, when we look at what is happening in this case, we could look at what is known as the oxidation state of everybody. And the oxidation state is really not necessarily the charge. In some cases, it is the same as the ionic charge we think about, like, -1 for Cl or +1 for sodium. In other cases, it's something different. And anything that is from the periodic table that is by itself, not attached to anybody else, has no charge or a zero oxidation state. So the sodium here would have a zero oxidation state, has no charge. Chlorine is a diatomic molecule. That is how it naturally comes. So it also would have a 0 for the oxidation state. Remember that they only gain charges, right, when they kind of hook up with other things. So when we get to the right-hand side here and we have our ionic compound, the sodium here has a +1 charge, and the chlorine here has a -1 charge. And if we look at, for example, here, we make a little number line, and we look at the sodium. The sodium on the left-hand side of the equation started at 0, which is right about there. And on the right-hand side of the equation, it ended at +1, which means it is moving to the right there towards the positive side. In this case, our sodium is going through oxidation. Now, when we look at the chlorine, it is starting at 0. And on the right-hand side, the chlorine is ending at -1, which means it would be moving in that direction on the number line, more negative, and it is going through reduction. By the way, I did not even need to do that if I feel good about oxidation for sodium. By default, the chlorine is going through reduction. They always happen together, so you really just have to identify one of them. Now, what does that mean? That means really in this case, what is happening is this guy is shooting some electrons over to the chlorine in this case. And again, that is the third reason why a reaction takes place. That is why this is a redox reaction overall that's happening. This is also classified again as a synthesis reaction because two things make one thing. Is another classification of this reaction. You can write what is referred to as half reactions for a redox reaction. And a half reaction is essentially half of the overall reaction that's taking place. When we look at the sodium here, it is actually losing electrons and becoming 2 sodiums with a +1 charge and giving off 2 electrons. This is what is known as the oxidation half reaction. And it's the oxidation half reaction because the electrons are always on the product side, like they are being given off. So that is how you know when you look at it that that is an oxidation half reaction. Electrons should always be on the right-hand side of the arrow, like they are being given off. When we look over here at the chlorine is going to pick up those couple of electrons and make 2 Cl minuses. And in this case, this is what is known as the reduction half reaction. The reduction half reaction will always have electrons on the reactant side, like they are being added, as opposed to here on the product side. By the way, how many electrons is each sodium losing? They're each losing 1 electron, and there's 2 of them, and that's why there are 2 electrons in that top half reaction. Each chlorine here is individually gaining 1 electron, which is why, again, those are 2 electrons. Now, these are called half reactions because if you add them back together, you get the overall reaction that is taking place. So since I'm running out of room here, I'm going to flip the page and rewrite those. So we got 2 sodiums going to 2 of these, plus 2 electrons, oxidation half reaction. We have our chlorine plus a couple of electrons going to 2 Cl minuses, our reduction. They are called, again, half reactions because if we add these reactions together, and whenever you go to add 2 half reactions together, an oxidation half reaction and a reduction half reaction, you always want to make sure that the electrons in each half reaction are the same number. So each half reaction should have the same number of electrons. Now, what happens if they don't have the same number of electrons? If they do not have the same number of electrons, before you add them together, you need to multiply that half reaction by a number. So if they're not the same, you need to multiply by a number. And that may require you to multiply one half reaction by a number. It may actually, in some cases, require you to multiply both half reactions by numbers to get it the same. So just as an example of that, let's just say we had a half reaction where we had 3 electrons in this guy, and we had another half reaction where we had 2 electrons in this guy, right? They are not the same number of electrons, which will prevent us from adding these together. But the common number between 3 and 2 is 6. So we would have to take this entire half reaction, whatever else is there. I'm not going to write anything else, but whatever else is there, we would have to multiply everybody by 2. And then we would have to take this half reaction and multiply everybody by 3. And that would then eventually get us 6 electrons in the first guy and 6 electrons in the second. And now we would be good to go to add these together. So it does sometimes require, like I said, you may just have to multiply one by a number. You may have to multiply both of them by a number. But before you add them back together to get the overall reaction, they do have to be the same number of electrons in each. The idea behind that is we are sending electrons from one substance to the next. So however many electrons somebody loses is the exact number of electrons somebody else should gain. So that's an important thing. In this particular case, I actually balanced it out to begin with, which means we do have the same number of electrons in each half reaction. So when we add these together, the way that we add these together is we first want to always make sure anything on opposite sides of the arrow that's the same can completely cancel out, or it can reduce down. So you can think of the arrow like an equal sign, like you're subtracting it over to the other side. So in this case, we have 2 electrons, which should always cancel out. And by the way, the electrons should always cancel out. And also the electrons in these half reactions should always be on opposite sides. So if you ever find yourself doing this and you got electrons on the same side, you screwed up. Yeah, so you got the wrong thing going on in that case. You always got to be on opposite sides. At this point, everybody on the left-hand side stays there. Everybody on the left-hand side stays, and everybody on the right-hand side stays there. I'm going to put those together because those are 2 ions that are going to come together basically to make sodium chloride, an ionic compound. Any questions on that there? So in a basic, simple sort of redox reaction where you have half reactions, the only thing you have to worry about is before you add those things back together, do you have the same number of electrons? Are they on opposite sides? Make sure they are the same number of electrons, and then add them together, cancel out whatever cancels out. Now, as we talked about before, this is the guy that is going through oxidation, and this is the guy that's going through reduction. There are 2 other words that sound very similar to this. They're sometimes confused by people, and that is there's things that are known as the oxidizing agent and the reducing agent. The oxidizing agent is the substance that gets reduced, while the reducing agent is the substance that gets oxidized. So why are they called that? They are called the oxidizing agent because when it gets reduced, the only way it could get reduced is to gain electrons. And the only way it could gain electrons is to cause somebody else to lose electrons. So it is causing somebody else to lose electrons. It is known as the oxidizing agent. The reducing agent is the one that gets oxidized. So when somebody loses electrons, that means somebody else has to gain electrons. And causing somebody else to gain electrons means you're causing it to be reduced, and it's known as the reducing agent. In this example right here, the sodium is our reducing agent, and the chlorine is our oxidizing agent. So it's basically opposite of what's happening. By the way, when you're asked what is being oxidized, what is being reduced, what is the oxidizing agent, the reducing agent, those are always found on the left-hand side of the arrow, on the reactant side. So you find all those things on the reactant side of the arrow. Any questions on that there? Okay. So how do we know about sort of oxidation numbers? By the way, when you have a situation like this, that is a metal and a non-metal coming together, right? And we know metals always do what with electrons? Gain or lose them? They lose them, right? So when you have a metal and non-metal coming together to make an ionic compound, it should always be the metal being oxidized because it should always be the one losing, and non-metals always gain them. So in an ionic compound formation like we have here, it's super simple to figure out oxidation and reduction because the metal should always be oxidized and the non-metal should be always reduced. But what happens if we had something like this where we had iron 3 on this side and we had iron 2 on this side of the arrow? Is the iron in this case being oxidized or reduced? Take a moment and think what you think it is. All right. Is it being oxidized? Is it being reduced? Is nothing happening to it? It's having a good time. Nothing's happening. Well, let's see. We could again use our number line here and see what's going on. So clearly the iron on this side is starting at +3 and ending at +2. So +3 is like here and +2 is heading in that direction. That means it's becoming more negative. So the iron here is actually being reduced or going through reduction in this case. By the way, that would mean in this case, the iron is the oxidizing agent in this case, yeah? Any questions on that there? So again, that's a nice thing about the little number line approach. Just got to know which way it's pointing, right? So more negative reduced, more positives being oxidized. Any questions on that? All right, so an important part of this, obviously, with redox reactions is understanding what is everybody's oxidation states and numbers. So let's talk about the rules for assigning oxidation numbers or states is sometimes referred to. So oxidation number states is what is sometimes referred to. And the oxidation number is, like I said, it's really the charge the atom would have based on sort of how it's sharing electrons, if it's covalently bonded, or in an ionic compound, how it's being transferred. And like I said, it is not always sort of the number you might think or are used to doing for certain elements. The first rule is what we just did. Anything that is basically just an element by itself, how it naturally comes, it's not combined with anybody else, will be an oxidation state of 0. When you have any type of monoatomic ion by itself, like we just did there with iron 3 or iron 2, whatever the charge of that ion is also its oxidation state. So lithium here has a +1, would be a +1. Iron 3 would have a +3 oxidation state. Oxygen, which I would say in most cases is the greatest place to start with when you're assigning these numbers, should probably always start with oxygen. It's a good place. Oxygen is going to be -2. And do you have a question? Yeah. It would be in that case like a +2 because it's bound together in that sense. Each individual one is +1, so overall it would be sort of +2 in that case. Yeah. So here, oxygen is a -2, and that usually is what is oxidation state. One exception for oxygen is if it's actually peroxide, which is a polyatomic ion. Like in hydrogen peroxide, it actually would be -1. So if you have hydrogen peroxide or something like that, it's actually -1. Other than that, it's usually a fairly safe bet to go -2 on oxygen, unless you got that kind of peroxide hanging out. By the way, when we do write oxidation numbers, we do include the pluses and the minuses with the number when we write them. So if the thing is a +2, you should not just write 2, you should write +2. Yeah. And if it's a -2, you should write -2 for the oxidation state. So you should include the charges with it. Now, other rules, the oxidation state of hydrogen is usually 1, +1, except if it comes after a metal. In that case, it's hydride, which means it's -1. everybody in group 1 is going to be +1. Everybody in group 2 is going to be +2. Fluorine is going to be -1. When you add up all the oxidation numbers together, it has to equal the charge on the compound. If it's neutral, it needs to add up to 0. If it has like a -1 overall charge, it needs to add up to -1. So for example, if we take our friend here, bicarbonate, and we want to assign oxidation states for everybody here, I would say most commonly here, if you got a 3-pack like we have here, I would start to the right, to the left, and leave the one in the middle for the end. Yeah, so leave the element for the middle to the end. I'm going to start with oxygen, which is -2. There are 3 oxygens, which gives us like a grand total of -6 when we take all 3 of them together. Going to the other side, we have hydrogen, which is +1. Now, in this case, it does have an overall charge of -1, which means when we add all these guys together, we need to actually end up with -1. In this particular case, if I just add up what I got going on so far, I have a -5, right? That means the carbon here is actually a +4 oxidation state, which gives me a -1 overall. So the hydrogen in this case would be +1. The carbon would be +4. And very important as well, the oxygen, if you were asked what is the oxidation state of oxygen in this thing, it is -2. It's not like the grand total of everything. So not -6, it would be -2. Any questions on that one here? Let's take a look at a few more examples. Let's see how we get there. So let's take a look here at Li2O. So once again, I'm going to start in this case with oxygen, which is -2. Lithium is group 1, which means it's just +1 like normal. This is an ionic compound, which means it's our normal sort of charges, if we want to think about it. Oops. So lithium here would be +1. Oxygen would be -2 in that case. Any questions on that one there? Now let's take a look at PF3 in this case. Once again, I'm going to start with kind of to the right there, the fluorine. Fluorine is always -1, so that's -1. Here we have 3 of them, which means it's -3. There is no charge here, which means it should equal 0 overall. That means the phosphorus in this case is actually going to be a +3, +3 in this case. +3 and -3 equals 0. And that means the oxidation state of phosphorus is +3, and the fluorine here is -1, yeah, in this case. If we take a look at nitric acid, once again, I'm going to start with the oxygen, which is -2. There are 3 of them, gives me a -6. My hydrogen here is +1. Once again, here, nitric acid is neutral, which means everybody here needs to add up to 0. In this case, to get us to 0, the nitrogen is actually rolling with a +5 in this case. And that gets us to 0. Now, you may be saying to yourself, when I do like ionic stuff, right, isn't nitrogen group 5 and has a -3 charge, along with our friend phosphorus, which has a -3 charge? And the answer is, yeah, it does in an ionic compound. So in an ionic compound, that is the charge and also the oxidation state. These guys are not ionic, right? This is covalently bonded, and they're sharing electrons, right? Between phosphorus and fluorine, which one's more electronegative? It is fluorine, which means when we have the phosphorus fluorine bond here, all 3 of those phosphorus are sucking out the electrons towards themselves, right? And as they suck the electrons out here in these unequal sharing of electrons, that is making our phosphorus now becoming more and more electron deficient and positive. And that's why in this case, when it's sharing electrons with somebody that's quite electronegative compared to itself, it's actually going to become more positive because those electrons are being shared. That's different than, for example, in a case where sodium sends an electron over to phosphorus and it picks it up and becomes fully negative, right? And that's what happens in an ionic compound. So sometimes people have a hard time wrapping around oxidation states and the charges that we have beat into your head in terms of ionic compounds. So it is still going to be what it is in an ionic compound like it was over here. But if it's a more covalent compound where we're sharing electrons, things that we normally think about as having like a negative charge can sometimes have a positive charge because of the unequal sharing of electrons. And that's the same thing here with our nitrogen. Same deal, right? We got nitrogen and oxygen. Oxygen is more electronegative, and it's going to suck those electrons out from the nitrogen as it's sharing electrons. That, in this case, for nitrogen, is going to make it a more positive sort of charge and oxidation number, different than when nitrogen is actually the one just receiving the electrons from a transfer and becomes negatively charged. So that is why these things, can have positive charges. Any questions on that there? So again here, hydrogen for this nitric acid would be +1, nitrogen would be +5, and oxygen would be -2. Lastly, a little dichromate action here, Cr2O72-. Once again, I'm going to start with our oxygen, which is -2. That gives us kind of like a -14 happening here. This has an overall charge of -2, which means when we're said and done, we need to add it up to -2. Also here for our chromium, we don't just have one, we actually have two of them. That means in this case, each individual chromium would have to actually have a +6 charge, because +6 and 2 gives us a +12, and +12 and -14 leaves us with a -2. So in this case, the chromium is +6 oxidation state, the oxygen is -2. Any questions on how to assign those? Super important when you're doing redox and balancing it, because you need to understand what is being oxidized, what is being reduced, and how many electrons are sort of involved in that. Any questions on that there? Okay. All right, so now that we know how to assign it, and we talked about just basic redox reactions where we add it together, like in your study assignment that you're going to have to do, you're actually going to have to balance some of these redox reactions in a little bit more complicated of a situation, which is either acidic conditions or basic conditions. And it requires a little bit more work to do that. So I'm just gonna, I think, give myself some extra room here. I think recopy it up here. So we have iron with a +2. We have a little dichromate here. And we're going to iron 3 and chromium 3. All right, so let's say we have this equation, and like I said there, we want to balance it in acidic conditions first. So we'll just talk about how to do it in acidic conditions. Probably the very first thing that you want to do is basically understand what is being oxidized and what is being reduced. So why don't you take a moment and decide what is being oxidized and what is being reduced in this case. So take a moment so you can figure it out. Again, you have to compare oxidation numbers on each side. So obviously you want to compare iron to iron on left and right, and chromium to chromium on the left and the right. Yeah. All right, so let's take a look. So comparing iron here, which has a +2 oxidation state because that's the charge of the ion. And we have the iron on the other side. Let's go above here, +3. We actually just did this guy a second ago. This is our dichromate that we did in the last example. We saw the chromium was +6 and the oxygen obviously was -2. And on the right-hand side here, our chromium is +3. So again, if we want to figure out what's going on, we could use our number line if you like. And if we look at the iron to begin with, our iron is starting at +2 here, and it's ending at +3, which means it's becoming more positive, and that means it's going through oxidation. So this guy here is going through oxidation. By default, what that means is our chromium is going through reduction, right? And we could also do for the chromium. The chromium on the left-hand side is +6, which would be way out here, perhaps, right? And on the right-hand side, the chromium is +3, which means it's moving to the negative side, and that tells us it's being reduced. But again, if you can figure out one, by default, the opposite thing is happening to the other thing. That would mean in this case, the iron is our reducing agent, yeah? And the chromium here, or the dichromate, is our oxidizing agent. So remember, the agents are kind of opposite of what is happening to those substances. First off, any questions on that identification? All right. Now we're ready to balance this thing in acidic conditions. So the first thing you really want to do is take your equation and break it up into the two half reactions, oxidation half reaction and reduction half reaction. So we have our iron goes with iron. So just keep it really simple. Same elements need to be in the same equation. We have our dichromate, which is chromium, goes with our chromium. Now, one of the nice things about identifying what is being oxidized and what is being reduced, I know that this is my oxidation half reaction and this is my reduction half reaction. So I got that all settled. All right, so now that we split it off, we're ready to start the balancing. The first thing we want to do is balance all elements except hydrogen and oxygen. And how do we balance all the elements except for hydrogen and oxygen? We balance them just like a normal equation. We put a coefficient. So when we look at the oxidation half reaction with the iron, there's one iron on the left and one on the right, so that's good to go. On the bottom, when we look at the chromium, there's two on the left and only one on the right, right? There's two here and only one here, basically. Not charges, actual, things that are there. So just like normal balancing equation, we're just going to put a coefficient in front. All right. And again, at this point, we are not concerned about oxygen or hydrogen. There's something special to balance those. So we're not really worried about those at this point. Any questions so far? So split it off into the half reactions, balance every element except for oxygen and hydrogen. Once you've done that, you are actually now ready to balance the oxygens. And the way in this method that we balance oxygens is we actually add water. And we add water to whichever side needs oxygen. So we add water to whichever side needs oxygen. Now, the problem with adding water is when I add water, which is oxygen, the other element that's with water is hydrogen. So for every water that I add, although it may fix the oxygen, I have now added more hydrogen. So whichever side needs the water gets the water added. Then to the opposite side, you add 2H pluses for every water that you add. So one side gets water to balance the oxygen, and to balance those hydrogens you just put in there, other side gets 2H pluses. I know. Who came up with this crap? I know, but we'll see. All right, so we don't have to worry about oxygen in the first one, right? Because there's no oxygen, right? So in the reduction one, we have 7 oxygens here, right? And we have none on the other side. That means the right-hand side will need 7 waters, and now 7 waters are going to give us 7 oxygens. But now how many hydrogens did I put over there? 14. So to make sure we're not short hydrogens, we need to go to the other side and we need to add 14 H pluses. Yeah. So water to one side, two H pluses for every water to the other side. The goal here is when we're all said and done to make sure this is balanced like a normal equation. Got the same number of elements and everybody on each side, and also the same charge on each side. Any questions at that point there? Now, clearly, if the top one has some oxygens, you would do the same thing. You would add some water to that, but obviously there is none. All right. At this point, we have balanced all the elements. We have balanced oxygen and hydrogen. And by the way, if you started with For example, if you started with, say, something like this, HNO3 on this side and maybe like NO2 on this side. And in this case, in addition to the oxygens that are not equal, there's also hydrogen that we're actually starting out with that's not equal. So if you have this situation where you kind of got an extra hydrogen or so on one side versus the other, you can, to the opposite side, just add an appropriate amount of H pluses, and that will get you all balanced. At some point, you'll have to do that. At some point, if you start out with unequal numbers of hydrogens on each side, you'll have to add the appropriate number of hydrogens. So sometimes it's just easier to do it up front and go, okay, I got 2 extra hydrogens on that side. I'm just going to add 2 H pluses at that side, and everything will work out okay. All right, so now that we balanced everything, we're now ready to balance the charge on each side of these half reactions. So we're going to balance the charge. And the way that we balance charges in this case is we add electrons. So electrons are negatively charged, which means we need to add the electrons to whichever side needs a negative charge to get us to equal. Now, the charge on each side of these half reactions do not have to be 0. They just need to be the exact same number on each side. The easiest way to do this is just think about overall charge. Sometimes people think about each individual sort of element and how many electrons it lost, and you're just going to get lost doing that. By the way, there's no need to do that because, as we just talked about, when you add up all the oxidation numbers of everybody that's involved, it equals the overall charge. So you should just look at the overall charge of everybody and you'll be able to do it really quickly. So what do I mean by that? I come over here on this side of the arrow, we have a +2. That's all we got going on, right? On this side of the arrow, we have a +3. Which side would need a negative charge to balance it out? Yeah, the product side would need 1 electron. This will give me a -1. +3, -1 equals +2 on the right, +2 on the left. Again, they do not need to equal 0 on both sides. They just need to equal the exact same charge on each side, yeah? Now over here, I got 14 +1s. That is a +14 for all those, right? This entire thing is a -2 charge, which means I don't care about everybody individually. That's a -2. That means overall here on the left-hand side, I have a +14 and a -2. That's a +12 working on the left-hand side when you add those together. I come over here, I have 2 and 3. That is a +6, right? You have 2 +3s is a +6. Water is neutral, 0. That is a 0. I have a +6 overall on the right-hand side. I have a +12 on the left-hand side. Which side needs the electrons? The reactant side on the left-hand side, right? We need how many to get us to the same number? Yeah, we need 6 electrons. That's going to provide a -6 and a +12. Gives us a +6 on the left and a +6 on the right. First off, any questions on that there? Now, how do I know I didn't really screw that up and I put the electrons on the correct side? I know that because, first off, they did end up on opposite sides, which is a good first start, right? But when we have an oxidation half reaction, right, what side should the electrons be on? Should be on the product side, which they are. So that's a good sign, right? And if I have a reduction half reaction, like we talked about earlier, the electrons should be on the reactant side. So that's why it's a really good idea at the beginning to figure out which one's your oxidation reduction. It does 2 things. Make sure you add the electrons to the correct side. And by the way, if you know which one's your oxidation reduction, you already know which side you should put the electrons on, right? Oxidation side should get the electrons on the products. Reduction should get it on the reactants. So again, just kind of doing that work up front can make some of this a lot better, yeah? Any questions so far? All right, the last thing we're going to do here is we want to add these half reactions together. Just like we talked about at the beginning here, before I could add these half reactions together, what has to be the same in each? The electrons, yeah? Are the electrons the same in each half reaction? They are not. In the first one, I have 1 electron. and the second one I have 6. So before I could add these together, I need to end up with 6 in each. In this case, I need to multiply the top reaction by 6. I don't need to do anything to the bottom reaction because it already has 6 electrons, right? So if I do that, and I think I'm going to copy it on the next page here. It's just a little crowded here, I think. So I got 2 plus 3 plus. So we got Fe2 plus, Fe3 plus, and we had 1 electron. And then on this side, we had 6 electrons, 14 hydrogens. 6 electrons plus 14 hydrogens plus a dichromate. And that went to our chromium with a +3 that had a 2 in front of it, I believe. And that should be everything. And 7 waters. There we go. All right. All right, so now I'm ready to do pretty much the last step, which is add these together. But before I could add them together, like I said, we do need to make sure we have the same number of electrons. So we're going to multiply everybody in that top one by 6, not just the electrons. So I'm going to write it underneath. That gives me 6 iron 2s, gives me 6 iron 3s, and 6 electrons. Now we are ready to add these back together. What should always happen, as we talked about, is the electrons should always cancel out. Opposite sides of the arrows, one's on the left, one's on the right, so they're going to cancel out. At this point, everybody on the left-hand side of the arrow stays there. Everybody on the right-hand side of the arrow stay there. So just writing there everything on the left, we have 14 H pluses plus Cr2O72 minus plus 6 of the iron 2. That is everything that is on the left-hand side of both arrows, yeah? Our equations. Now we're just going to put everybody on the right-hand side of those arrows on the right-hand side. That is 2 Cr3 pluses plus 7 waters plus 6 iron 3s in this case. Now, if I did not screw up, I should now have a balanced equation in acidic conditions. So this should be balanced in acidic conditions. Equation, acidic conditions. Now, how should this be balanced? This should be balanced 2 different ways, like a normal equation, which means I have 14 H's there, I have 14 H's there. I have 2 Cr's there, I have 2 Cr's there. I have 7 oxygens there. I have 7 oxygens there. I have 6 irons there. And I have 6 irons there. So it is balanced like a normal equation. The second thing that needs to be balanced is the overall charge on the left-hand side of the arrow needs to be exactly the same charge as the right-hand side. So let's just add it up here. That's going to give me a +14 for my first guy there. That's going to give me a -2. That is 6 times +2 is a +12. That is a lot of math at this late hour, but that is a +24. I think if I didn't screw that up, happening there on the left-hand side. On the right-hand side, that is 2 times +3 +6. That is 7 times 0, which is 0. That is 6 times 3, which is 18 pluses. +18 and +6, I hope is +24. So we are balanced in both ways correctly. So when you're done with these, it needs to be balanced just like a normal equation, exact same elements on each side. Overall charge on the left and right needs to be the same. Again, they do not have to be 0 on both sides. Any questions on that? This is acidic conditions. You are also sometimes asked to balance it in basic conditions. And there are a couple ways you could do that, but probably the easiest way to do it is what we just did, which is balance it in acidic conditions. And at the very end, just turn it into basic. So you can kind of do everything we just did and then turn this guy into a basic equation. So I'm going to do that by just erasing the top here. So I don't have to recopy it again on another page. Let me just get rid of some of this up here, and we'll turn this guy basic in a second here. All right, so we can get rid of those. All right, so obviously if you had to balance this in basic conditions, you're just going to follow the exact same procedures we just talked about and get yourself a balanced equation in acidic conditions. Now, to turn this into basic, you're going to add OH minus to both sides of the arrow. And the amount of OH minus you're going to add is equal to the number of H pluses you have. All right, so let's take a look at my equation here. I have how many H pluses? I have 14. I am then going to add 14 OH minuses to both sides. So I'm just going to do that up here and write it in. So I'm going to have 14 OH minuses to the left. I'm going to still keep everything the same that was there. And again, I'm adding it also to the other side. So it's going to be added not to just one side, but in this case, to both sides. So we're going to add it to both sides. Again, equal to the amount of H plus that we had. All right, so now that we did that, when you have OH minus and you have H plus, what does that make? Makes water, yes? So those 14 OH minuses and those 14 H pluses on the left-hand side will come together to make 14 waters. Yeah? And usually at this point, when you're turning it into basic, you will have some waters on the other side, which we do, right? We have 7 waters on the right-hand side. We got 14 waters on the left-hand side. You could then reduce this down. 7 minus 14 leaves you a net of 7 waters on the left-hand side of the equation. Then everything else stays exactly the same. So obviously you don't do the H plus or OH minus because that was your water you combined. And you will end up with this. And if you do all that, you are now balanced in basic conditions. So the easiest way to turn to basic is just do it acidic, add the equal amounts of OH minus to both sides, combine water, reduce down the waters, and you'll be there. Still should be balanced the exact same 2 ways. 14 H's, 14 H's, 7 oxygens there plus 7 more is 14. 14 oxygens, 6 irons there, 6 there, 2 chromiums, 2 chromiums. Overall charge on the left, 0, minus 2, plus 12 gives you a plus 10. This side, plus 6, plus 18, and a minus 14. So that's a minus 14, leaves you a plus 4 and a plus 10. Plus 6 gives you a plus 10 on both sides. So we are still balanced on both sides. First off, any questions on that there? How do you know it is acidic in the first one and basic in the second? Well, an acid is something that has an H plus. So H plus in the equation, acidic, yeah? The second equation doesn't have H plus, but it has what makes something a base. It has OH minus, makes it a basic. So if you see H plus in one of these at the end, you know it's acidic. If you see OH minus at the end, it is basic. Any questions on any of those steps there? All right, let's take a look at one more here together just to make sure. Not this one, it's the one we just did. All right, we'll do this one here. We write up on top. So we have I minus plus MnO4 minus I2 and MnO2. All right, so again here, we're going to do this basic as well just to see the whole thing again. We're going to identify what is happening here. So we look here at the iodine, that is -1. The MnO4 here, I'll do on the bottom, that's -2 for the oxygen. There's 4 of them. Gives you a -8. Overall, this is -1. The Mn in this case, to get us to -1, is actually +7 in this case, yeah. And again, +7 and -8 is -1 overall. I2 is how it naturally comes, which means it has oxidation state of 0. We usually write it up on top, but that's okay. Oxygen here is -2. There's 2 of them, gives you a -4. This is neutral, which means it should add up to 0. That means in this case, the Mn here to get us to 0 would be +4. Yeah. So if we look at our number line here, and we look at the I is starting at -1, which is here, and ending at 0, which means it's moving in a positive direction. And that means that the I- here is going through oxidation. If we look at the Mn here, it is starting at +7, which would be out here, and ending on the right-hand side at +4, which means it is moving in the negative direction, which means this guy here is going through reduction. That would mean that the I- is my reducing agent, and the MnO4 is my oxidizing agent in this case. Any questions on that? So again, as I mentioned earlier, especially with redox, understanding oxidation numbers and how to assign them is really critical to understanding what is happening. All right, so we're ready to balance this one. Again, we're just going to take common elements together. So we're going to go half reactions, I- to I2. They both have I's. MnO4- and MnO2, they both have Mn, so they stay together. We have already now identified that this guy is my oxidation half reaction. This guy is my reduction half reaction, right? Now that we split it off, the next thing we do is balance everybody but oxygen, hydrogen. So in the case of the I do need to do that. I have 2 I's on the right, only 1 on the left. So we do need to put a big 2 in front of it. How about for the Mn? Are we okay? We are okay. We have 1 Mn on both sides. So again, we're not concerned at this point about the oxygen. Now that we balance everything but oxygen and hydrogen, we're ready to add our waters to balance the oxygen. I don't have to worry about the top one, right? Because there's no oxygen. On the bottom one, this one has 4 oxygens. This one has 2 oxygens. Which side needs the water? Left or right? The right-hand side needs 2 waters. That's going to supply us the oxygen that we need. Because we added 2 waters to the right, that means we over-hydrogenated it. So to the left-hand side, we would have to put 4 H pluses. So at the end, we're not short hydrogens at this point. Any questions up to there? Now we're actually ready to add electrons, right? Now we already identified this, but we'll look at overall charge. This is -2 and this is 0. That means the side that needs the negative is the right-hand side. And I know that because this is the oxidation half reaction. So I can feel very confident that I should put 2 electrons on that side to give me a -2 here and a -2 here. We're good, yeah. Coming down here, this is +4. This entire thing is -1. That leaves you a +3 overall on the left. This is 0, and this is 0, which means which side needs the electrons? The left-hand side, right? And I know that because of this as well. And in this case, we need 3 electrons. That gives us a -3 and a +3, gives us a 0 on the left and a 0 on the right. So we added our electrons. Any questions on that? And again, by identifying that earlier, you kind of know which side you should put the electrons on. We are now ready to add them back together, but just like previously, we need to make sure electrons are the same, and they are not in this case. Common number between 3 and 2 is 6. So in this particular case, we actually have to multiply not one of the half reactions, by a number, but both half reactions by a number. So the goal here is to get everybody the same number of electrons. So I'm going to do that. I'm just going to erase all my oxidation numbers here so it's not so messy-ish here. Do that, get rid of that there. All right, so we're going to take, I'll go there. We're going to take the top half reaction, and because we need to get it to 6, we're going to take this entire thing, and we're going to multiply it by 3. That's going to give us 6 electrons. We're going to take the bottom equation and multiply by 2, and that's going to give us 6 electrons there. So I'm just going to rewrite everybody underneath. We'll kind of do a little squiggly line maybe. All right, so multiplying that 3 across gives me 6 I minuses, goes to 3 I2s and 6 electrons. Multiplying that 2 across gives me 6 electrons, 8 H pluses, 2 MnO4 minuses, and 2 MnO2 and 4 waters. Yeah. And now we're ready to add these together. Once again, electrons should always completely cancel out. So again, if you get to a point where the electrons do not completely cancel out, you screwed up somewhere on the balancing or adding or something like that. They should always be completely gone. At this point, again, everybody on the left stays on the left-hand side of the arrow. Everybody on the right stays on the right. And I'm going to go 8 H pluses plus 2 MnO4 minus plus 6 I minus. So that's everything on the left-hand side of the arrow. We're going to arrow over here and go 3I2 plus 2 MnO2 and 4 waters. By the way, at this point, I'll put a box. That is our balanced equation in acidic conditions. I do see an H plus, so it's balanced in acidic conditions. And just quickly doing a little counting, 8 hydrogens on the left, 8 on the right, 2 Mns on the left, 2 on the right, 8 oxygens on the left, 4 in the second one and 4 in the first one. It gives us 8. 6 iodines on each side. Overall charge here on the left, we have a plus 8 from that guy, a minus 2, and a minus 6. That is 0. And that is 0. That's neutral. That's 0. And that is 0. So we are balanced again, just like we should be. We have the same number of elements on each side and also the same overall charge on each side. Any questions on that there? Now we were looking for basic, so again, we pretty much just do acidic, and at this point we can now turn this into basic. And I'm just going to erase the top part here and just recopy it up on top. So let's get rid of this here. All right, so we're going to add our OH minuses in this case. As we talked about, we're going to do it to both sides, right? So that is the goal there. So in this case, we're going to add OH minus to both sides to turn this basic. And the amount of OH minus we're going to add is the amount of H pluses that we ended up with. So in this case, we ended up with 8 H pluses. So we will add that in on the left-hand side, 8 OH minuses to go with our 8 H pluses that were there. And now I'm just going to copy everything that was there. So I'm not changing anything other than just recopying it, basically. And to the other side, everything stays the same. And again, here we've got our 4 waters. And remember, when we're going basic, we need to do it to not just one side, but add that OH minuses to both sides. Once again, the side that has the OH minus and the H plus will give us 8 waters in this case. And now we're down to just reducing it down. So 4 waters on the right-hand side will leave us 4 waters here on the left-hand side. So 4 waters is what we're left. And now everything else starting here is the same. So 2 MnO4 minus, 6 iodide, 3 I2, 2 MnO2, and 8 OH minus. And now this should be our balanced equation in basic conditions. I know it's basic because I see OH minus there. Once again, should still be balanced both ways. We got 8 hydrogens on the left, 8 on the right, 4 and 8 oxygens on the left, so that's 12, 8 and 4 on the right, 2 MNs on both sides, 6 I's on both sides. Overall charge here, 0, -2, -6, overall -8 on the left, 0, 0, and -8 on the right. So we're balanced in both sides. And that is the goal when you do redox. It should be balanced normally, like an equation, and charge should be balanced on each side. Yeah. Say again? How did I get the 4 H2Os? Yeah. It's because originally here we had 8 waters when we combined the H pluses and no H minuses. And on the right-hand side, we had 4 waters. So basically just subtracting it to the other side. Yeah. Other questions? All right. Fun stuff, huh?